let's go another layer deeper and look at the link layer. Our goals for this are to understand the principles behind the link layer services, so looking at error detection and correction, sharing broadcast channels, link layer addressing, and local area networks. We'll look at instantiation and implementation of various link layer technologies. Let's start with an introduction. Before we can begin, it's pretty important to make sure that we know all the terminology we'll be using when we discuss the link layer. First off, hosts and routers are going to be referred to as nodes. These are all the steps that you have to go through as you send data over the network. The communication channels that connect these nodes on any given path are called links, which you might suspect. These links could be wired, they could be wireless, you could have a cell phone tower that connects to your phone, they could be local area networks, and so on. And the packet that we're talking about at the link layer level is called a frame, and it encapsulates a datagram. Now you may see the term here, data link layer, and wonder, well, what's the difference between that and the link layer? Depending on the model of layers that you're looking at, whether it's OSI or if it's TCP/IP, some of these refer to the second level as the link layer, some refer to it as the data link layer. When we talk about data link layer, we're really just talking about the responsibility of transferring datagrams from one node to a physically adjacent node over the link. Some models like the TCP/IP model may merge this layer along with the physical layer when they're talking about how this data gets transferred. But in general, we're not quite talking about things at the wired level just yet. Although many of our discussions we're going to have with link layer are going to combine a little bit with what's going on at the physical level. So how does the link layer really operate? The link layer, as I mentioned, is responsible for transferring datagrams, which may use different link protocols over different links. So you may start off with your computer, which is plugged into an Ethernet cable, which then uses frame relay after it gets past the router, and then eventually reaches maybe a wireless hotspot, which then could connect to your phone. And through that whole process, you may have used a bunch of different protocols to actually get from start to end. Each of these protocols have different services available. Some might have reliable data transfer, some might not. And one way to think about this is akin to considering if you were taking a trip from Princeton, New Jersey to Lausanne, Switzerland. If you're going on your trip, it's very unlikely that you're going to have just one link that takes you straight there. You might have to take your fancy limo from Princeton, New Jersey to JFK Airport. From the JFK Airport, you take a plane to Geneva. From Geneva, you could take a train that gets you to Lausanne. And so as you went there, you, the tourist, are representing the datagram. The mode of transportation that you take is the link layer protocol in this instance. And the actual way to figure out how you got there in the first place, the routing algorithm, represents like a travel agent if you were actually using one of those, although I don't think many of us do these days. So what are some of the services offered at the link layer? First off, we have framing. So datagrams are encapsulated into frames, which then can add headers or trailers, things that are needed for managing any link layer protocols. If there is a shared medium, let's say multiple hosts are using the same link at the same time, MAC address, which is medium access control, are used, which can help you to not only manage the protocols, but also identify source and destinations in a way different from an IP address is, and we'll get to that in a little bit. In addition, link layer offers reliability between adjacent nodes. So we've seen a little bit of this when we were back at the transport layer looking at RDT. However, when it comes to something like a wireless link, very often these can have high error rates, whereas something like a fiber or a twisted pair cable is less likely to have this. So in an attempt to, and the reason that you would have reliability both at the transport layer and the link layer is that when it comes to managing something like a wireless link, you might want to correct your errors locally once you realize there is an error at the link level, rather than waiting for the entire process to go from sender to receiver and realize, oh, something was missing, gotta send it again. Doing things at the link layer, specifically for something like a wireless link, can save you a little bit of time. It can be a bit more efficient. Some more services we have available include flow control. We've kind of seen this already in other layers, which is the pacing between sending and receiving. Error detection and correction, which is a little bit interesting in that sometimes at the link layer you can notice that a 1 has been changed to a 0 or vice versa. And when these are detected, you can immediately get the sender to resend a transmission if needed, or drop a frame if you realize there's something wrong with it. More tricky than this is not only detecting but also correcting some of these bits, but it is possible to do so without having to retransmit from the sender if you notice that very specific bits happen to be out of order. Finally, there is a difference between half duplex and full duplex devices. Full duplex devices can have a link sending in both directions at the same time, whereas with half duplex, nodes at both ends can transmit, but only one can be sending at a given moment. So where does the link layer actually exist? Where is it implemented? Well, every host and node has an implementation of the link layer, usually in an adapter. So way back when, you would actually need to get an Ethernet card, a network interface card that has everything you need to connect to the internet. Nowadays, most of that is usually built into your motherboard, so it's probably on a chip right now if you're watching this on a PC or on a laptop. The adapter is responsible for handling the physical side of things and implements the link layer itself, whereas some of the parts of the link layer that have to do with things like addressing, the software side of things essentially, are still handled by the CPU. So really the link layer is both a combination of hardware, software, and firmware implemented in multiple parts of a host system. So here's what it looks like when two adapters are communicating with one another. The sending host, which is on the left side here, takes its datagram, encapsulates it in a frame, adds things like error checking bits, reliable data transfer, flow control, and so on, and sends it over to the receiving host on the right side here, which looks for errors that it's received, does the reliable data transfer, flow control, so on. And once it gets this datagram, it extracts it from the frame and passes it to the upper layer at the receiving side. So let's take a look at how the link layer implements error detection and error correction. So here's a quick diagram to illustrate what error detection looks like. Here, EDC is short for error detection and correction bits. So this is just a bit of redundancy you add to hopefully catch mistakes. And D here is the data that's protected by the error checking, which may include header fields, for example. Now, error detection is not always reliable. You may miss some errors, but this is like a rare occurrence in general. The larger the EDC field, however, the better detection and correction that you can have. So for any given datagram that has D data bits, there is a section of there's a section included for error detection and correction. This gets sent along a bit-prone error link along the bottom, and when it reaches the receiver, it receives its own data bits and its own data error detection and correction bits, and then it tries to see, do all of these bits actually make sense with regards to the error detection and correction bits that were sent? If so, deliver the datagram. Otherwise, we've detected an error. So one way to implement error detection is through parity checking. This is where you literally just look at whether the sum of the bits is even or odd, and you use another bit to keep track of that value. So you have D data bits here, the ones you can see, plus maybe some more on the left and so on. And after adding all of the bits individually up, like 1 plus 1, so on and so forth, if you find it's even, you set the parity bit to be 0. If it's odd, you set the parity bit to be 1. And then for error detection, you just check and see, is the sum of these bits, does that match the parity bit? You can improve on this a little bit by doing two-dimensional bit parity, which also helps you to detect and correct single bit errors. So if there is a single mistake, there actually is a way that you can potentially fix it. The way that this is done is by taking the data and putting it into rows and columns, and then looking at the parity of the rows as well as the parity of the columns. And if you see that there's a mismatch, then you know exactly which bit causes the problem. So here's a brief example here of what this might look like. Let's suppose you have this set of data, so you have 10101, 11110, 01110. If you do the rows across, you can see these are the parity bits here. If you do the columns along the bottom, these are the parity bits that are there. And you also can have another parity bit that checks to see that there is that you have the parity of the rows in total. Now, if we look at this example here, where we see that this 1 has been changed to a 0, so on the left here it was a 1, on the right here there's an error and it was flipped to a 0. If we have all of these parity bits here, we actually can see that, well, The row and the column that don't actually make sense are row 2 and column 2. We can see we have 1, 1, 1, that's 3, but our parity bit says it should be a 0, so obviously this row has a problem. Where in the row is the problem? Well, this column seems to have an issue because there's only a 1 here, but the parity bit says it's a 0. So you can use this to pinpoint exactly which bit has the mistake and flip it back if there is a single bit error. So just to briefly review, we've already talked a little bit about internet checksum. This is used to detect errors, which are flipped bits in a transmitted packet, used generally at the transport layer. So the sender takes transport segment contents, represents it with a sequence of 16-bit integers, and the checksum is the addition of the segment contents, and you take the ones complement sum. The sender puts this checksum value into the UDP checksum field, and the receiver makes sure that it actually is the right addition. If the number does not add up, then obviously there's definitely an error. If the number does add up, then no error is detected. This doesn't mean there is no error, it just means that you didn't find one. A more powerful way to detect errors is using CRC, which is cyclic redundancy check. This is a more powerful form of error detection, which uses a bit more math to figure out whether or not, same problem as before, D data bits actually have an error in them. So the way that this works is that you take your data bits, represent them as a binary number, and you choose something called a generator, which is a bit pattern that starts with a 1 and then has a format that the sender and the receiver both can agree on. When you have your generator, you then choose R bits, so capital R here, of a size lowercase r. These bits are then appended onto your data set. So then the idea is that D with the R bits on the right side is exactly divisible by your generator using modulo 2 arithmetic. So modulo 2 arithmetic here, we're ignoring carries and we're just doing XOR operations, because in binary addition and subtraction pretty much give you the same result, right? 1 and 1 gives you 0, 0 and 1 gives you 1, whether it's subtraction or addition if you ignore the carries. So we're just doing the XOR operator. Since the receiver knows the generator, it divides the data bits appended with the R bits at the end by the generator. If there is a non-zero remainder, you know there's an error because there's a bit somewhere that wasn't in the right spot. If there is a 0 remainder, then everything is okay. And this is used to detect burst bit errors widely in practice with things like Ethernet, Wi-Fi, and so on. And so the mathematical formula you can see at the bottom is D times 2 to the power of R XORed with R. Here's an example of the math used in CRC. In this example, we have a generator that's 1001. The extra bits that we're adding onto our data bits D is, there's going to be 3 extra bits. And the problem that we're trying to figure out is, well, what are the 3 bits that we append to the end to make sure that what we're sending is divisible by G? In order to solve this out, you actually just have to work through the division process. The way that you can do this is you take your data bits here, you add just zeros to the end, and calculate what the remainder is after you divide by your generator G. So after doing some of the math, we eventually find that our remainder is 0, 1, 1. So this means that what we actually end up sending across is going to be 1, 0, 1, 1, 1, 0, 0, 1, 1. And this whole 9-bit sequence is then going to get received by the receiver, who is then going to divide that number by 1001. And you might want to try this math out for yourself just to make sure that in the end the remainder of that should be 0. For more details on the math, you can check out the link at the bottom. But the ultimate idea here is to make sure that the division actually works out, and if it does, then everything was sent correctly. Otherwise, you know that there's a mistake. Next, let's take a look at multiple access protocols. So when it comes to access links, there's 2 different kinds that you can have, either point-to-point or broadcast. Point-to-point is something like point-to-point protocol you could use for dial-up access, or a link between an Ethernet switch and its host, which is different in that you can only have 2 people talking to each other across that link, compared to something like broadcast, which is either a shared wire or medium like Ethernet, LAN, where you can have multiple devices using that link at the same time. So cabled internet, you can see on the left here, shared radio frequency like Wi-Fi, a shared radio frequency like satellite, or, people at a cocktail party just talking in the air all at the same time. So multiple access protocols come into play when you have a single shared broadcast channel where multiple nodes need to be transmitting at the same time. This is where interference can happen. You might have a node that's receiving multiple signals at the same time from different senders. And so multiple access protocol is an algorithm that talks about how do nodes actually share this channel? When is a node allowed to transmit versus when does it have to wait? Now this communication about sharing the channel is going to have to use the channel itself. There's no secondary source you can use for coordination. So an ideal protocol for multiple access is if you're given a broadcast channel that has R bits per second, when one node wants to transmit, it can just send at that rate, R. However, when M nodes want to transmit, each one is only allowed to send at an average of R over M bits per second. This is fully decentralized. You don't need to coordinate anything. There's no synchronization of clocks or slots, and it's very, very simple. Now, when it comes to multiple access control protocols, there's three general classes that we're going to talk about. One is called channel partitioning. This is where you break up a channel into smaller pieces, which could be time slots or frequency, and you allocate a piece to a node for its exclusive use. You're allowed to use this part of the channel, in other words. Random access is where instead the channel is not divided, and instead you just allow collisions to happen. And rather than worrying about who's sending at what times, you just make sure that there's a way that you can recover when these collisions happen. And then finally, the last class is taking turns, where each node is allowed to send when it's their turn. When their turn is over, the next node is allowed to send. However, some nodes that have more to send are allowed to take longer turns to get their information across. Let's start by taking a look at channel partitioning. So the idea with channel partitioning is that we give divided access to different nodes with regards to the channel. So first off, let's start with one way to do this, which is through time division. So each of the different stations gets its own fixed length slot. So this is how much time you're allowed to send stuff in each round. So let's say that we have 6 slots here. This is a LAN where there's 6 different places that packets can be sending from, and 2, 5, and 6 aren't going on. So what will happen is number 1's allowed to send for 1/6 of the time slot, so is station 3, so is station 4, and then after the 6 slots have gone by, you repeat the process. So then 1 can continue sending, 3 can, and so on. Any of the unused slots just go idle, nothing just happens during that time. So you can see this is perfectly fair in that no station is allowed to send more than any of the others, but obviously there's some limitations with regards to being able to use the full channel to its maximum capacity. Another way to divide up the channel is using frequency division. So the idea here is that you take the frequency of the channel, the bands that are actually within, say, a cable, and split it up among the different stations. So number 1, 3, and 4 all get their own specific frequency bands that they're allowed to send stuff along, splitting up the cable into, for instance, 6 different slots. Just like time division, this has sort of the same problem in that any of the unused frequency bands just aren't doing anything. So this means that in the case where you only have one node that's actually sending stuff out, it's using the full bandwidth of this divided by how many total stations that might be serviced, meaning there's no real way for a single node to take advantage of the full bandwidth of, for instance, this cable. Next, let's look at random access protocols. So the idea here is that whenever you have a packet to send, you just transmit at full power across the channel with no coordination going on whatsoever. Anytime you do have 2 or more transmitting nodes, this is when collisions are going to happen. So random access protocol is about how to detect when these collisions are occurring and how do you recover from them, for instance, by retransmitting if you need to. Some examples of these protocols include slotted Aloha, and the variations on CSMA. Let's start by taking a look at slotted Aloha protocol. So there are some assumptions that go on here. First off, all the frames have the same size. The protocol is going to divide time slots, each of which are basically equivalent to how much time it takes to send one frame. Transmissions only happen at the start of a slot. You don't have something happen like partway through a slot. All the nodes are synchronized, so they know what these time slots are. And if two or more nodes are transmitting in the slots, then both of them, or more than two of them, if all of them are there, detect that the collision is happening. So how does the protocol work? Basically, when a node gets to a fresh frame, it transmits in that slot. If there's no collision, great, you can just keep sending and continue onward. If there is a collision, then you basically flip a weighted coin and you decide randomly, okay, should I try again now? Or with some probability P, you try to figure out whether or not you should start sending again at the beginning of any subsequent slot. And eventually at some point you say, okay, I've randomly decided here's when I'm going to start to send again in a hope to avoid more collisions. So here's an example of slotted aloha in practice. At the beginning, all of them all start sending, so obviously a collision happens. So then they have to randomly decide to wait and see, okay, well, when can I actually send? Let's randomly decide. Node number 3 doesn't randomly decide things happen right away. It's gonna basically flip the coin and get tails a few times too many. Nodes 1 and 2 randomly decide, okay, let's start in the third time slot here. Oh, there's another collision again. Okay, I guess we're gonna try another time. Then node number 2 randomly selects immediately the next one to go and says, oh look, I actually was able to send it now. Okay, so I will send it. Great, there's a success. Continuing onward, randomly nothing is happening here. Node 2 is already done, so it's happy and out of the way. And at this time slot, there's another collision again. Oh no, 1 and 3 randomly decided that they would start sending here, but there's a collision, so that doesn't work either. 1 waits a little bit, and so does 3. 1 randomly decides, all right, let's start sending it here. And there's no collision, so it's sent successfully. And then node 3 finally randomly decides that it'll send it here. So what are the benefits of this? The main benefit is that if there's just a single node that's transmitting, it's able to use the full rate of the channel the whole way because there are no collisions to worry about. It just can use all of the power. This is highly decentralized. Only the slots need to be synchronized. You obviously need to know when these time slots are, but that's the only synchronization really that needs to happen. And it's very, very simple. On the cons, collisions you can see here cause a lot of wasted slots to happen. It took all of this time just to send these three data bits, so that's obviously a big problem. You have idle slots where nothing is happening, and you do need to have the clock synchronization between all of the nodes. So let's take a look at the efficiency of slotted aloha. Let's suppose we have many nodes, all that have a lot of frames to send, so we want to look at the throughput divided by the bandwidth. We have n nodes here. The probability each one transmits in a given slot is p, which means the probability that a given node has success in a slot is p times 1 minus p to the power of n minus 1. And the probability that any node has a success is the same thing multiplied by how many nodes there are. So when it comes to the maximum efficiency, we want to find the probability that maximizes this equation, right? So turns out that what you should select is 1 over how many nodes there are. Kind of makes sense. So that means that the maximum efficiency is, here you can substitute in 1 minus 1 over n all to the power of n minus 1. And so as the number of nodes goes to infinity, the maximum efficiency you have is 1 over e, which is 0.37. So in other words, this channel is really only used for useful transmissions 37% of the time. So what if we decided to just throw away the slot idea completely? We keep something simpler with no synchronization and use what's called pure or unslotted aloha. As soon as a frame arrives, you just send it right away. Obviously, this means the probability of a collision goes a lot higher because now, since you're not always starting things at the same time, you might have a frame that overrides with the end of another one or the beginning of another one, and so on. But what's the efficiency of this look like? Well, when it comes to the probability of success for a given node, it's the probability that a node is able to transmit times the probability that no other node is transmitting in that time period times the probability that no other node is transmitting on the right half of that time period. So if we go back really quickly to our time frame here, first off, we need to make sure nothing is starting anywhere within this side on the left, and also that nothing is starting on this side on the right. So we have two frames where nothing can really begin, otherwise there's going to be a problem. We either have something overlapping at the beginning or something overlapping at the end. Now, if we do all the math here, what do we end up with? Well, this is the formula that you get for it. It's the first probability times the second one times the third one. If we do a little bit of math, we can combine these two. If we choose the optimum probability and see what happens as n goes to infinity, well, we end up with 1 over 2e, which is half as good as we were doing with slotted aloha. That's not too good either. Another way we can try is by using CSMA. So this is carrier sense multiple access. And the idea here is that we listen before we decide to transmit. If it seems like the channel is idle, we just go and send our frame. It's probably okay to do so. If the channel that we look at seems like it's busy, we defer the transmission and wait to see what's happening. So in human words, don't interrupt other people when they're talking. Now, CSMA is not perfect, and collisions can still occur, even if you're listening for what's happening on channel. Because of the delay in time that it takes for one node to hear another one, it may be the case that two of them begin transmitting when they think the channel is empty, but really it's not. So in this little diagram, we have time going from top to bottom, and we may have our nodes spaced out from left to right. And so at the beginning, this node decides it's going to start sending a message, but that message doesn't actually reach the node on the right until a point after that node has thought the channel is empty and it should start transmitting. So when this happens, the whole packet time transmission is wasted, a big problem, meaning you have to consider distance and propagation delay when it comes to determining the probability of collisions happening. So we can improve a bit on CSMA by adding in a bit of collision detection. By doing this, we can detect collisions within a short amount of time and immediately abort sending a frame that we know is being interrupted by somebody else. When it comes to wired local area networks, you can do this pretty easily by measuring signal strengths, comparing transmitted and received signals, but it's a little more difficult when you're handling things wirelessly because the signals that you're receiving are always going to be, or almost always, going to be weaker than the ones that you're sending out. Your local transmissions are going to be stronger. When it comes to a human analogy, think about someone who is talking in a room and someone else starts talking around the same time. If you're a polite conversationalist, which is what you would be if you're trying to be CSMA with collision detection, as soon as you hear someone talking at the same time as you, the polite thing to do is pause and wait for either them to go first or to figure out who should be talking at the time. So here's what CSMA with collision detection looks like from the perspective of the network interface controller and adapter when you're working with Ethernet. First off, the controller gets a datagram from the network layer and it creates a frame that it's going to send through the channel. If the channel seems like it's idle, you send it. If the channel seems like it's busy, wait until it's idle and then retransmit. If it can transmit the whole frame and there's no collisions that are detected, great, we're all done. However, if there is another transmission detected while you are transmitting, you immediately abort and send a signal to say, hey, I am talking right now, we need to stop. After this aborting happens, the network interface controller enters something called binary or exponential backoff. The idea being the amount of time that you wait before you retransmit increases as more collisions actually happen. So after the mth collision, you choose a random number, k, between 0 and 2 to the power of m minus 1. And so the network interface controller waits for k times 512 bit times and then goes back to step 2, trying to see if the channel is idle and so on and so forth. This means that as more collisions have happened, there's a longer interval before you wait and start again trying to send out your message. So what's the efficiency of this algorithm look like? Well, if we have t sub prop to be the max propagation delay between two nodes, and t sub trans to be the time to transmit the max size frames, then our efficiency is 1 over 1 plus 5 times t prop over t trans. So the efficiency goes up as this the propagation delay goes to 0, and efficiency goes up as the time to transmit goes to infinity. So this has better performance than Aloha. It's simple, it's cheap, and it's decentralized, all things that we want in our ideal random access protocol. Now let's compare these protocols to taking turns. When it comes to channel partitioning, the channel is shared fairly and efficiently even when there's a very high usage load. However, at low loads, it's not so great. You only have 1 over n bandwidth even when there's only one active node. With random access protocols, you kind of have the reverse problem where at very low loads, the single node can fully utilize the channel, which is great. But when there's high loads, there's a lot of collisions that are happening, a lot of overhead. So the goal of taking turns is to try to look for the best of both these worlds. So one way to implement taking turns is with polling. You have a single node, which is your master node, and it invites the others to transmit in turn. Usually means that these nodes are sort of dumb and aren't doing any calculations on their own. So the master polls and says, okay, you can talk, and then polls again, says, okay, you can talk. Concerns with this are that the polling itself obviously has some overhead, latency can be an issue, and if there is a problem with this master, then the whole thing kind of falls apart. So instead of using a master node, another approach is using what's called token passing or a token ring. And the idea here is you have a control token which is passed sequentially from one node to the next, meaning that you're now allowed to be sending the message. So if this node down here has some data to send, the token starts it over here, token gets passed along, this node has nothing to send, and once the token eventually reaches here, the data can actually be sent out. Obviously, some concerns for this are, first off, there's overhead in managing this token, latency still remains a problem, and now the point of failure, instead of being a node, is just what happens if something goes wrong with the token. So just to summarize some of the protocols that we've talked about so far, we have channel partitioning, where we can break down either by frequency or by time what parts of the channel we're actually using to make sure there are never any collisions. Random access control, which is dynamic collisions could happen, but we try to mitigate them as much as possible. This includes Aloha, slotted Aloha, CSMA, CSMA with collision detection. In some technologies, this can be very easy, like wired, but it's a little bit harder in some, like wireless. Ethernet uses CSMA with collision detection, whereas Wi-Fi uses collision avoidance, where basically instead of just transmitting, you transmit the intent to transmit to make sure you're not talking over others. And then finally, taking turns can come from either polling using a central master site or using token passing. Bluetooth is an example of a technology that uses polling, whereas fiber distributed and token rings are both examples of token passing.